Welcome to Orbit into Sleep. I'm so glad you found your way here tonight. Wherever you are in the world, whether you're tucked up under a heavy duvet, lying in the dark with your phone propped on the pillow, or just hoping your mind will finally kindly decide to switch off, you are in exactly the right place. Tonight, we are going on a very gentle journey together, far, far away from here. Past the moon, past Mars, past Jupiter and Saturn, all the way to the very edge of our solar system, to one of the most beautiful, mysterious, and honestly quite surreal places we know of. We're going to talk about diamond rain. Yes, real diamonds, falling like rain inside a planet. I promise you, this is not a dream. Well, not yet anyway. Over the next little while, I'm going to share some of the most quietly wonderful discoveries that scientists have made about what happens deep inside the ice giant planets, Neptune and Uranus. These are places so remote, so strange, so utterly unlike anything we'll ever see with our own eyes, that thinking about them has a way of making everything else feel very, very small. And sometimes, when everything feels very small, it's just a little bit easier to let go and drift off. So get comfortable, let your shoulders drop. If you haven't already, close your eyes or let your gaze go soft. There's nothing you need to do right now, nowhere you need to be. Tonight, we're just going to float together through some of the most beautiful ideas in science and let your mind carry you gently into sleep. Before we begin, though, a small kind favor. If you're enjoying Orbit into Sleep and you'd like other restless minds to find their way here too, a like and a subscribe helps more than you might think. It's how the universe of the internet helps people discover things that are good for them. So if you feel moved to do that, we would be truly grateful. And while you're feeling sociable, do leave us a little comment letting us know roughly how many hours of sleep you normally get on a good night. Are you a solid 8-hour sleeper, a restless 5? We're genuinely curious, and we read every single one. Right then, let's begin. Let's talk about diamonds and the deep dark hearts of distant worlds, where the rain is made of diamonds. Let's start right at the beginning with the most important question of all. Is diamond rain real? For a long time, scientists weren't entirely sure. It was one of those ideas that lived in the space between theory and proof, something the math suggested was possible, something the imagination found irresistible, but something that nobody had actually seen with their own eyes. It lived in textbooks as a compelling idea, a hypothesis, a probably, maybe, we think so, but that has changed. In the last few years, and I mean quite recently, researchers have moved diamond rain from the category of interesting theory into something far more exciting. It has become an observed reality, something that has actually been witnessed happening in a laboratory under conditions designed to mimic the crushing, searing interior of a distant planet. And the planet at the heart of this story is Neptune. Now, Neptune is not a planet that gets talked about very much. It's the 8th and furthest planet from the Sun in our solar system, and it has a way of being overlooked. Jupiter gets all the attention with its great red storm. Saturn charms everyone with its rings. Even Mars feels familiar to us now, with its rovers trundling across the rust-colored dust. But Neptune is something else entirely. from methane in its upper atmosphere, which absorbs red light and reflects back the most gorgeous, aching blue you can imagine. If you could somehow hover above Neptune and just look down at it, scientists believe it would be one of the most visually stunning things a human being could ever witness. It sits about 4.5 billion kilometers from the Sun. The light that reaches Neptune is so faint that a sunny day there would feel darker to us than a deeply overcast winter afternoon here. It takes Neptune 165 Earth years to complete a single orbit of the Sun. When it was discovered in 1846, it hadn't even completed one full lap by the time the Voyager 2 spacecraft flew past it in 1989. That brief flyby, lasting just a matter of hours, is still the only time a spacecraft has ever visited. We know remarkably little about it, which makes what we do know feel all the more precious. Neptune belongs to a category of planets called ice giants. Now, don't picture ice the way you might think of it. The word ice here is used by scientists to describe a particular mixture of compounds, primarily water, ammonia, and methane, that exist under such intense pressure and heat deep inside the planet that they behave in ways nothing on Earth ever does. They become exotic, strange, something altogether different from anything in our daily experience. Beneath Neptune's atmosphere, which is already a violent and churning place, there is a vast mantle of this planetary ice. It stretches deep into the interior, thousands of kilometers thick, under pressures and temperatures that are almost impossible to relate to anything familiar. And it is inside this mantle, in that crushing, superheated darkness, that something extraordinary begins to happen. Methane, which is a molecule made of one carbon atom bonded to 4 hydrogen atoms, finds itself under conditions so extreme that those bonds simply cannot hold. The carbon and hydrogen are pulled apart, the hydrogen escapes, and the carbon, now free, begins to do what carbon does under enough pressure. It forms diamonds, not one or two, not a scattering. Scientists believe that billions upon billions of tiny diamond crystals are forming constantly deep inside Neptune, and that once they form, they begin to fall. They sink through the mantle, slowly, inexorably, under gravity. Diamond rain descending through the interior of a planet in the dark, billions of miles away, right now as you lie here. For decades, the assumption was that this process only happened very deep inside the planet. Scientists believed you would need truly colossal pressures, around 100 times what was thought to be needed, and temperatures exceeding 5,000 degrees before a diamond could begin to form. That placed the rain very far down in the deepest, most inaccessible layers of the interior. But then something changed. Researchers, most notably a team that included scientists called Mungo Frost and Daniel Patrick Spears, ran a series of experiments using some of the most powerful tools in modern science. They used something called the European X-ray free electron laser, which is a facility that can generate X-ray pulses so brief and so intense that they can take what amounts to a snapshot of matter in the middle of transforming. In timescales so short, they are almost beyond imagining. These researchers were able to watch what happened to carbon under pressure. And what they found surprised nearly everyone. Diamonds weren't forming only at those crushing extreme depths. They were forming much higher up in what scientists call the shallower regions of the mantle, at pressures and temperatures far lower than the old models had assumed. The diamond rain wasn't a rare, deep, marginal event. It was more widespread, more pervasive, more significant than anyone had given it credit for. This discovery changed the story of Neptune in a fundamental way, because if diamonds are forming higher up in the planet, they have farther to fall. They spend more time sinking through the mantle, and all of that falling, all of that movement through the deep interior of a world turns out to matter enormously. It matters for how hot Neptune is. It matters for the strange and chaotic shape of Neptune's magnetic field. It matters for understanding why Neptune behaves so differently to its near twin, Uranus, which in many ways looks similar but acts almost nothing alike. We'll come to all of that. There is so much to explore here, and we have all the time in the world tonight. For now, though, just sit with that image for a moment. A vast blue world at the edge of our solar system, spinning slowly in the cold dark, its interior alive with the quiet, constant fall of diamonds. A process that has been going on for billions of years. A process that is happening right now, tonight, while you rest here and breathe and let the day dissolve. There is something genuinely soothing about that thought, I think. The universe has its own rhythms, its own slow and patient processes, and none of them require anything from you at all. You can simply be here, warm and still and resting, and on we drift, when chemistry becomes magic. So we know that diamonds are forming inside Neptune, but how exactly does a molecule of methane become a diamond? What actually happens in that deep, dark interior to turn something as ordinary as natural gas into one of the hardest, most brilliant substances in the universe? The answer is a story about chemistry under pressure, and it is, in its own quiet way, one of the most beautiful things I know. Let's start with methane, because methane is where it all begins. You may know methane as the gas that comes from natural processes here on Earth. It's in natural gas, it's produced by wetlands, it's even, rather charmingly, produced by cows. It's not a substance we associate with glamour or spectacle. It's a humble molecule. 1 carbon atom, 4 hydrogen atoms, bonded together in a simple, stable structure. But stability, it turns out, is a matter of context. On Earth, at the pressures and temperatures we live with every day, methane is perfectly content to exist as a gas. Those bonds between the carbon and the hydrogen hold. The molecule goes about its business undisturbed, but take that same molecule and place it inside the mantle of Neptune, where the pressure is millions of times greater than anything on the surface of our planet, and the temperature is thousands of degrees, and everything changes. Under those conditions, the bonds between carbon and hydrogen simply cannot survive. They break. The molecule is torn apart. The hydrogen atoms escape, floating off as lighter compounds rising away through the surrounding material, and the carbon atom, now liberated from its hydrogen companions, finds itself alone under extraordinary pressure, with nowhere to go but inward. And carbon, when it is alone and under enough pressure, has a very particular way of arranging itself. It forms diamonds. This process, the breaking apart of carbon and hydrogen bonds and the subsequent coming together of carbon atoms into a crystalline structure, is called dissociation and nucleation. It sounds technical, and in its details it is, but the essence of it is simple and almost poetic. Molecules are pulled apart by the violence of the environment, and from the pieces, something new and ordered and beautiful assembles itself. Now here is where it gets even more interesting. The interior of Neptune is not made of pure methane. It is a rich, complex mixture. Water is there in enormous quantities. Ammonia is there too. And it turns out that these other substances are not passive bystanders in the story of diamond formation. They are active participants. They are, in the language of chemistry, catalysts. Scientists discovered this partly through a rather wonderful experimental accident. In trying to recreate the conditions inside an ice giant planet, researchers used a material called polyethylene terephthalate, which you might know better by its everyday name, PET plastic. It's the material used to make plastic drinks bottles. The reason they used it is that PET contains carbon, hydrogen, and oxygen in proportions that do a reasonable job of approximating the mix of molecules inside a planet like Neptune. And when they subjected PET to the extreme pressures and temperatures of their experiments, something interesting happened. The oxygen in the plastic made a difference. It helped separate the carbon from the hydrogen more efficiently. It lowered the energy required to get the process started. In other words, oxygen made it easier for diamonds to form. This was a genuinely significant finding. It suggested that diamond rain inside Neptune isn't just driven by pressure and heat alone. The chemistry of the surrounding environment matters enormously. The water molecules present in the mantle, which of course contain oxygen, are likely acting as a kind of chemical helping hand, nudging the carbon along its path toward crystallization. And water wasn't the only catalyst the scientists found. Ammonia, which contains nitrogen, was found to reduce the temperature at which diamond formation begins by around 100 degrees. 100 degrees might sound modest in the context of a process happening at thousands of degrees overall, but in terms of where in the planet diamond rain can begin, it's actually quite significant. It means the rain can start in slightly cooler, slightly higher regions of the mantle than it otherwise could. So the picture that emerges is a wonderfully complex one. Diamond formation inside Neptune is not a simple, single ingredient process. It is a collaborative event driven by pressure, yes, and by heat, but also shaped and enabled by the chemistry of everything else that happens to be present. The water, the ammonia, the methane, all of them interacting together in ways that scientists are still working to fully understand. There is something I find deeply lovely about this. The idea that something as extraordinary as diamond rain is not produced by one dramatic force alone, but by a quiet cooperation of ingredients, each one contributing something, each one making the whole thing possible in a way that none of them could manage alone. And there is one more thing worth mentioning here, something that I think is quietly extraordinary. When a diamond forms inside Neptune, it doesn't remember what it was before. Think about that for a moment. A methane molecule, or a more complex hydrocarbon, goes through this violent transformative process. The bonds break. The atoms rearrange, new structures form, and the diamond that emerges at the end of this process has absolutely no record of its origin. Whether it came from methane, or from a more complex molecule, or from something else entirely, the resulting diamond is identical. Pure carbon arranged in its crystalline lattice with no trace of what it used to be. Scientists describe this as the molecule losing its memory during the transition. I think that is one of the most quietly philosophical things in all of science. The idea that transformation can be so complete, so total, that the past simply disappears. What you were before leaves no trace in what you become after. There is something very restful about that, I think. The idea of transformation without remainder. Change that is clean and complete and whole. Let yourself feel that for a moment, if you'd like. The day you had, the week you've carried, the thoughts that have been circling. None of them need to come with you into sleep. Sleep, in its own gentle way, is a kind of transformation too, a nightly renewal, a dissolving of the day into something softer and quieter. You are safe here. Your body knows what to do. And somewhere very far away, diamonds are forming in the dark, patient and unhurried, as they have been for billions of years. Just breathe and let yourself drift a little further. The many faces of carbon. We've talked about how diamonds form inside Neptune and the remarkable chemistry that makes it possible. But I'd like to spend a little time now on something that I think is genuinely underappreciated, and that is just how extraordinary carbon itself is as an element. Because carbon, you see, is a shapeshifter. Most elements behave in one way. They have a structure, a set of properties, and that's more or less that. But carbon is different. Carbon has this remarkable ability to arrange itself in completely different ways, depending on the conditions it finds itself in. And each arrangement produces something that feels almost like an entirely different substance. You are already familiar with two of carbon's most famous forms, even if you've never thought about them side by side in quite this way. The first is graphite. Graphite is the soft, dark gray material in the center of a pencil. It's the material that leaves a mark when you write. It's slippery, almost greasy to the touch, and not particularly impressive to look at. If you held a piece of graphite in one hand and a diamond in the other, you would be holding the same element in two completely different moods. Because diamond, of course, is the other famous form of carbon. And diamond could not be more different from graphite. Where graphite is soft, diamond is the hardest naturally occurring substance we know of. Where graphite is dull and gray, diamond is transparent and brilliant, scattering light into every color of the spectrum. Where graphite will smudge onto your fingers, diamond will scratch almost any other material without itself being marked. Same element, completely different character. The only difference is the way the carbon atoms are arranged. In graphite, carbon atoms are arranged in flat sheets, loosely stacked on top of each other. The bonds within each sheet are strong, but the connections between the sheets are weak, which is why graphite flakes apart so easily. In diamond, every carbon atom is bonded tightly to four neighbors in a rigid three-dimensional lattice, and it is this structure, this precise and particular arrangement, that gives diamond its legendary hardness. But here is where things become genuinely fascinating, because inside Neptune, the story of carbon doesn't stop at ordinary diamond. The conditions in the deep interior of an ice giant are so extreme that carbon can be pushed into forms that are essentially unknown on the surface of our world. Forms that are stranger, harder, and more exotic than anything in a jewelry shop. The first of these is called Lonsdaleite. It's sometimes known as hexagonal diamond, and it is, in its own way, quite wonderful. Ordinary diamond has a particular pattern to the way its atoms are stacked, a repeating sequence that scientists describe as ABCABC. Lonsdaleite has a different stacking pattern, an ABAB arrangement, which gives it a hexagonal rather than cubic crystal structure. It's a subtle difference at the atomic level, but the consequences are significant. Lonsdaleite is predicted to be up to 58% more resistant to stress than ordinary cubic diamond, 58% harder than the hardest thing we normally encounter. On Earth, Lonsdaleite is found occasionally at meteorite impact sites, where the violence of the collision briefly recreates the kind of extreme conditions needed to form it. But inside Neptune, those conditions exist continuously, deep in the mantle, meaning Lonsdaleite may be quietly accumulating there in quantities that dwarf anything we've ever found on our own planet. And if you go deeper still, deeper than where Lonsdaleite forms, the pressure climbs to levels so extreme that carbon may transition into yet another phase, one that doesn't even have a familiar name yet. Scientists call it BC8 carbon, after its body-centered cubic crystal structure. This phase is purely theoretical at present, a prediction made by mathematical models rather than something directly observed in a lab. But the models are confident. At the right pressure, carbon should be able to arrange itself into this structure, which is predicted to be even harder than diamond, even harder than Lonsdaleite. Harder than the hardest thing. It's a sentence that shouldn't be grammatically possible, and yet here we are. But wait, because the story of carbon inside Neptune has one more chapter, and it is the strangest of all. Go deep enough. Push the pressure up to truly extraordinary levels, around 1 trillion pascals, and raise the temperature to 50,000 degrees or more, and something happens that feels almost like a betrayal of everything diamond stands for. Diamond melts, not just softens, melts, becomes a liquid, and not just any liquid. At these conditions, the carbon becomes a metallic fluid. It conducts electricity. It flows. It behaves nothing like the clear, hard, brilliant crystal we associate with diamond, and everything like a strange, dark, shimmering sea. Scientists believe that deep inside Neptune, in the very deepest regions of the mantle where these extreme conditions are met, there may be an ocean of liquid carbon, a dark, metallic sea kilometers deep in the interior of a planet billions of miles away. And here is the detail that I find the most poetic of all. In this liquid carbon ocean, if it exists, diamonds may float. Think about that image for a moment. An ocean of liquid carbon, so dense and so strange that solid diamonds are less dense than the surrounding fluid, and so they float on its surface or drift within it, like icebergs in a dark and alien sea. Diamond icebergs in a carbon ocean inside a blue planet at the edge of the solar system. I genuinely do not know how to make that sound more beautiful than it already is. The universe has simply done it for us. Now, alongside all of this, scientists have also been investigating something a little more unexpected: the role of sulfur. Neptune's interior contains hydrogen sulfide, the same compound responsible for the smell of rotten eggs, which is a slightly unglamorous detail in an otherwise very glamorous story. But sulfur, it turns out, has a complex relationship with diamond formation. At lower pressures, sulfur actually helps carbon form diamonds, encouraging the methane to break apart and the carbon to aggregate. It is, in that range, another helpful catalyst in the story. But at higher pressures, something counterintuitive happens. Sulfur starts to bond with carbon instead, and this actually prevents the carbon from forming diamonds. The very thing that helped at one depth becomes an obstacle at another, which means that in sulfur-rich regions of Neptune's interior, there may paradoxically be fewer diamonds than in the surrounding areas. The universe, as ever, is more complicated and more interesting than any simple story we try to tell about it. What I love about all of this is the way it speaks to the hidden richness of things. Carbon, which we encounter every day in pencils and barbecue charcoal and the soles of our shoes, turns out to have this extraordinary secret life under pressure. Given the right conditions, it becomes the hardest thing in the world. Given more extreme conditions, it becomes something harder still. And under the most extreme conditions imaginable, it melts into a dark metallic sea where diamonds float like ice. There is something in that which feels like a gentle reminder that things are rarely only what they first appear to be, that there are layers always, that the ordinary contains the extraordinary, waiting quietly for the right conditions to emerge. You contain depths too, you know, quiet, unhurried depths. And right now, in the stillness of wherever you are, you don't need to be anything other than exactly what you are. Let the thoughts go soft. Let the images of those distant crystal structures, those exotic forms of carbon forming in the dark, drift through your mind like slow, heavy snowflakes. You're doing beautifully. Just keep breathing. The planet that shouldn't be so warm. There is a mystery at the heart of Neptune that has puzzled scientists for decades. And like so many of the best mysteries, it becomes more interesting the closer you look at it. Here it is, stated simply. Neptune is too warm, not warm in any way you could feel, of course. Neptune is an extraordinarily cold place by any human standard, with cloud-top temperatures around minus 200 degrees Celsius. But when scientists measure how much heat Neptune radiates out into space and compare it to how much energy it receives from the sun, the numbers don't balance. Neptune radiates approximately 2.6 times more energy than it receives. That extra heat has to come from somewhere. Something inside Neptune is generating warmth continuously and has been doing so for an extraordinarily long time, long enough to still be going billions of years after the planet formed. And when you look at Uranus, Neptune's near twin, the mystery deepens further still. Uranus and Neptune are remarkably similar in many ways. They are close in size. They have similar compositions. They are both ice giants, both blue, both sitting in the cold outer reaches of the solar system. If you were designing two planets to be alike, you might well produce something like this pair. But Uranus radiates almost no internal heat at all. It receives energy from the sun and it emits roughly the same amount back. There is no significant extra warmth coming from within. Where Neptune glows with internal energy, Uranus is, thermally speaking, almost silent. Why would two such similar planets behave so differently? This has been one of the great unanswered questions in planetary science for a long time, and the discovery of diamond rain, and particularly the recent finding that diamond rain occurs at shallower depths than previously thought, offers what many scientists now believe is a compelling answer. Let's think about what happens when a diamond forms inside Neptune. A tiny crystal of carbon comes into being deep in the mantle. It is denser than the surrounding material, much denser in fact. Diamond has a density of around 3,500 kilograms per cubic meter. The surrounding mantle material, the planetary ice mixture of water and ammonia and methane under pressure, has a density of roughly 1,500 kilograms per cubic meter. The diamond is more than twice as dense as its surroundings. So it sinks. Not quickly, not dramatically, but steadily, pulled downward by Neptune's gravity, which at the surface is about 1.5 times stronger than Earth's. The diamond crystal falls through the mantle, slowly descending toward the core. And as it falls, it releases energy. This is a principle that operates everywhere in the universe, from raindrops falling to Earth to asteroids plunging into planets. When something falls under gravity, it converts potential energy into other forms of energy, primarily heat. The falling diamond warms the surrounding fluid through friction as it moves through it. And because Neptune's mantle is vast, and because diamonds have been forming and falling continuously for billions of years, the cumulative heat released by this process is enormous. Scientists have worked out the mathematics of this, and the numbers are striking. With a mantle mass of roughly 3.5 times 10 to the power of 26 kilograms, which is an almost incomprehensibly large number, and a settling distance of around 10 million meters through which the diamonds fall, the gravitational potential energy released is more than sufficient to account for Neptune's observed excess heat. The diamond rain, falling silently in the dark interior of the planet, has been warming Neptune from the inside for billions of years, and it shows no sign of stopping. Now, this also helps explain the difference between Neptune and Uranus, though the full explanation there is still being refined. One leading idea is that Uranus may have a stable layer in its interior, a region that doesn't mix and convect the way Neptune's interior does. If heat generated deep inside Uranus cannot flow upward through this stable layer, it would be trapped, never reaching the surface to be detected. Neptune, with its more actively churning interior, can move that heat around and eventually radiate it outward. The diamond rain in this picture is not just a beautiful phenomenon. It is a heat engine, a geological mechanism that has been running continuously since the early solar system, powered by nothing more exotic than gravity and the density difference between diamond and ice. There is something almost meditative about that image, a process so patient, so slow, so utterly indifferent to time. Diamonds forming and falling and generating warmth over billions of years in the dark interior of a world that most people have never thought about for more than a moment. And the warmth it generates has consequences that reach all the way to Neptune's surface. Neptune has the fastest winds in the solar system, winds that reach speeds of around 1,000 miles per hour, far faster than anything recorded on Earth, far faster than Jupiter's famous storms. Those winds are driven in part by the internal heat rising up from the interior, working its way outward through the planet's layers until it reaches the atmosphere and sets it into violent motion. So in a very real sense, the diamonds falling quietly in Neptune's deep interior are connected to the howling storms in its upper atmosphere. The microscopic and the planetary, linked by the patient conversion of gravity into heat into motion. There is also something quietly wonderful about the efficiency of it all. Neptune's carbon content in the mixtures scientists use to model its interior is around 10.7% by mass. That's a significant fraction of the planet's total composition, and the models suggest that the carbon available is more than sufficient to sustain the observed heat output, not just for the age of the solar system so far, but potentially for billions of years into the future. Neptune is not running out of diamonds. It is, in all likelihood, still making them right now, tonight, while you rest. Somewhere out there, in the deep cold of the outer solar system, a tiny crystal of pure carbon is forming in the dark. It catches no light because there is no light to catch. It makes no sound. It simply exists for a moment in the process of becoming, and then it begins its long, slow, unhurried fall. And in falling, it gives off a little warmth, which somehow, in a roundabout and rather marvelous way, connects it to the storms on the surface of a blue planet billions of miles from here. and to you, lying here in the warmth of your bed, breathing slowly, letting the day dissolve. The universe is generous with its warmth, even in the places where you'd least expect it. You're doing so well. Just let yourself sink a little deeper into that warmth now. There's nothing to hold on to, nothing to work out, just the quiet and the dark and the distant sound of diamonds falling. The scrambled compass. If you've ever used a compass, you'll know that it points north. Reliably, dependably, always north. That's because Earth has a magnetic field that is, broadly speaking, quite orderly. It has a North Pole and a South Pole, and while it wanders a little over geological time, it is recognizably a dipole field. Two poles, roughly aligned with the planet's rotation, generating a field that wraps around the Earth in smooth, elegant curves. It is the kind of magnetic field you would design if you were designing one from scratch. Sensible, organized, neat. Neptune's magnetic field is none of those things. Neptune's magnetic field is, and I mean this in the most affectionate way possible, an absolute mess. It is not aligned with the planet's rotation. It is tilted at an angle of around 47 degrees from Neptune's rotational axis, which already makes it rather unusual. But more than that, it doesn't even pass through the center of the planet. The center of Neptune's magnetic field is offset from the planet's geometric center by a significant distance, more than half of Neptune's radius away from the middle. It's as though someone took a perfectly good magnetic field and nudged it sideways and then tilted it and then decided that was fine and left it that way. The result is a magnetic field that is asymmetrical, chaotic, and deeply puzzling. Different parts of Neptune's surface experience dramatically different magnetic field strengths. The field doesn't behave the way a simple two-pole system should. It has multiple poles, lobes, and irregularities. A kind of magnetic complexity that scientists describe as non-dipolar. Uranus, intriguingly, has exactly the same problem. Its magnetic field is also dramatically tilted and offset, also asymmetrical and complex, also completely unlike the tidy fields of Earth, Jupiter, or Saturn. For decades, nobody had a really satisfying explanation for why the ice giants should have such peculiar magnetic fields. There were models and hypotheses, but nothing that felt truly convincing, nothing that tied together the observations into a clear and coherent picture. And then came the diamond rain. The key to understanding Neptune's magnetic field turns out to lie in a remarkable substance called superionic water. This is another one of those things that sounds like it might be the invention of a science fiction writer, but is, in fact, perfectly real, experimentally confirmed, and genuinely extraordinary. Superionic water is what happens to water under the kinds of pressure and temperature found deep inside an ice giant. Under these conditions, the oxygen atoms in the water molecules lock themselves into a rigid, solid crystal lattice. They stop moving. They hold their positions as firmly as atoms in any solid. But the hydrogen atoms do something completely different. Rather than staying bonded to their oxygen partners, they break free. They become unmoored. They flow through the rigid oxygen lattice as freely as particles in a liquid, carrying their electrical charge with them as they go. So superionic water is simultaneously solid and liquid. The oxygen is frozen in place, but the hydrogen is flowing freely. It is a state of matter that sits between solid and liquid in a way that has no equivalent in everyday experience. And because the hydrogen ions are charged particles moving through the material, superionic water conducts electricity exceptionally well. It is, in other words, the perfect material for generating a magnetic field. Magnetic fields are generated by moving electrical charges. This is one of the foundational principles of electromagnetism. In Earth's core, liquid iron flows and generates our magnetic field. In Neptune's mantle, the flowing hydrogen ions in superionic water do something similar. They create electrical currents, and those currents produce a magnetic field. This is Neptune's magnetic dynamo. Now, here is where the diamond rain comes back into the picture in a beautiful and unexpected way. When diamonds form in the mantle and begin to fall, they don't just passively drift downward. They move through the superionic water layer, and as they do, they disturb it. They drag surrounding material with them. They create currents and flows in the conductive fluid. They stir the dynamo. And because the diamonds, thanks to the recent discoveries we discussed earlier, are forming at shallower depths than scientists previously assumed, they are stirring a much larger volume of the superionic water layer. The churning influence of the falling diamonds extends through more of the mantle, affecting more of the conductive material, driving more complex currents. Complex currents produce complex magnetic fields. The irregular, multipolar, offset magnetic field of Neptune may be, at least in part, a direct consequence of the diamond rain stirring the superionic water layer in a complicated, asymmetric way. The diamonds fall unevenly, driven by the uneven distribution of carbon-rich material and the varying chemistry of the mantle. That uneven stirring drives uneven currents, and uneven currents produce the scrambled, tilted, offset magnetic field that puzzled scientists for so long. There is also a secondary effect which is wonderfully subtle. As diamonds form and fall, they remove carbon from the surrounding fluid. The mantle material that remains behind is now slightly different in its composition. It has less carbon in it, and that change in composition affects the density and the electrical conductivity of the remaining fluid, which in turn affects how freely the hydrogen ions can move through it. So the diamonds are not just stirring the dynamo, they are also gradually and continuously changing the properties of the material the dynamo is made of, altering the very medium through which the magnetic field is generated, shaping the field not just through their movement, but through their absence, through the gaps they leave behind in the chemistry of the mantle. It is a feedback loop of remarkable elegance. The diamonds form and fall and stir and leave gaps, and all of those effects together produce and sustain and shape the magnetic field that wraps around the planet, a magnetic field generated by falling diamonds. I don't think anyone could have predicted that, and yet, here we are, and the evidence points clearly in that direction. Neptune's magnetic field, strange and messy and beautiful as it is, may be a direct portrait of its interior. a signature written in magnetism of all the complex chemistry and physics happening deep inside. When scientists measure the field from space, they are, in a sense, reading a message left by the diamond rain. I find that idea genuinely moving. The thought that something invisible, something you can only detect with sensitive instruments, carries within it the imprint of processes happening in an unreachable interior. That the surface of a thing can tell you something true about its depths, if only you know how to read it. And maybe that's worth sitting with for a moment as you rest here tonight. The idea that the quiet processes happening inside things, the slow and patient workings that nobody can see directly, leave their mark on the outside in ways that can eventually be understood. Your own quiet interior, the slow and patient thoughts unwinding as you drift towards sleep, the gradual relaxing of everything that was held tight today. None of that is visible to anyone, but it is real and it matters, and it is doing exactly what it needs to do. Let it happen. Let the interior do its work. The compass doesn't need to be neat to be pointing somewhere worth going. You're drifting beautifully. Just keep going. Before we continue our gentle journey through the cosmos, I just wanted to take a quiet moment to mention something. If you're finding it hard to sleep regularly, and that's brought you here tonight, it might be worth taking a look at our description. We occasionally update it with things that have genuinely helped other people with their sleep, whether that's something to read, something to listen to, or something small to try. No pressure at all. It's just there if you'd like it. Right then, back to the stars, listening to a planet ring. We have talked about what diamond rain is and how it forms and what it does to Neptune's heat and magnetic field. And all of that knowledge has come from a combination of mathematical modeling, laboratory experiments, and the brief, precious data gathered by Voyager 2 during its few hours of close encounter back in 1989. But there is a question sitting quietly underneath all of this, one that scientists are increasingly turning their attention toward. How would we ever know, directly, that diamond rain is actually happening inside a real planet right now? Would destroy any instrument we could, build long before it got anywhere near the interesting depths. We cannot drill, we cannot sample, we cannot look, and yet there may be a way to listen. The science of listening to planets is not new. Here on Earth, seismology, the study of how seismic waves travel through our planet's interior, has taught us almost everything we know about the structure of Earth's deep layers. We know that Earth has a solid inner core and a liquid outer core, not because anyone has ever been there, but because earthquake waves travel through those regions in particular ways, bending and slowing and reflecting according to the properties of the material they pass through. The waves carry information about the interior. You just have to know how to read it. A planet, when it is disturbed by a significant seismic event, doesn't just shake locally, it rings. The whole body vibrates in complex patterns like a bell struck by a hammer. These vibrations are called normal modes, and they are specific to the planet's internal structure. The frequencies at which a planet rings depend on the density, elasticity, and layering of its interior. Change the interior, and you change the ring. Scientists have theorized that if Neptune has a thick layer of diamonds accumulating around its core, that layer would have a very distinctive effect on the planet's normal modes. Diamond is extraordinarily rigid. It transmits sound and seismic waves much faster than the surrounding planetary ice. A diamond shell deep inside Neptune would act like an acoustic mirror, reflecting certain frequencies and allowing others to pass through, creating a characteristic pattern in the planet's seismic signature. Laboratory measurements of diamonds' acoustic properties are quite remarkable. In small diamond structures, researchers have measured what they call wineglass modes, particular resonant vibrations, at frequencies of around 19 kilohertz. The quality factor of these vibrations, a measure of how long the ringing persists before fading, is over 500,000. That is extraordinarily high. It means diamond rings and keeps ringing for a very long time before the energy dissipates. On a planetary scale, the frequencies would be far lower, shifted down into the millihertz range, or even lower, into what scientists call infrasound, frequencies below the threshold of human hearing. But the principle is the same. A diamond layer inside Neptune would leave its mark on the way the planet vibrates. Detecting those vibrations is another matter entirely. From Earth, or from a spacecraft in orbit around Neptune, picking up the subtle normal mode oscillations of a distant planet is an enormous technical challenge. It would require instruments of extraordinary sensitivity, maintained in position for long periods, gathering data patiently over months or years. We do not currently have a mission capable of doing this at Neptune, and it will likely be some decades before we do. But the ambition is there, and the theoretical framework is being developed, and that in itself is a kind of quiet progress. There is also another acoustic angle to this story, one that is perhaps even more evocative. The process of diamond formation itself, the nucleation of tiny crystals and their subsequent fall through the mantle, may generate sound. As diamonds move through the surrounding fluid, they displace material. They create pressure waves. The friction of a dense crystal moving through a viscous medium generates disturbances that propagate outward as acoustic signals. Individually, each tiny diamond contributes an almost unimaginably small amount of sound. But there are, at any given moment, an almost unimaginably large number of diamonds forming and falling inside Neptune. Their collective acoustic contribution might be detectable, in principle, as a kind of deep, subsonic hum emanating from the planet's interior. Scientists have drawn a comparison here to proposals for exploring other planets acoustically. There are designs being developed for balloon-borne acoustic receivers that would float in the atmosphere of Venus, listening for the infrasonic signatures of Venus quakes propagating up through the planet. A similar approach, adapted for Neptune's very different atmosphere, might one day be able to detect the acoustic fingerprint of the diamond rain itself. Imagine that for a moment. A balloon drifting in the upper atmosphere of Neptune, listening to the planet, and somewhere in the data it collects, buried in the noise, the faint and ancient sound of diamonds falling. We are nowhere near being able to do that yet. But the fact that we can conceive of it, that we can work out what we would need to hear and design in principle the instrument that might hear it, feels like a kind of reaching, a slow, patient extension of human curiosity towards something genuinely unknown. There is something in this whole thread of the story that I find particularly soothing. The idea of listening, the idea of patience, the idea that understanding doesn't always come from direct observation and dramatic discovery, but sometimes from sitting quietly with sensitive instruments and waiting for the universe to speak in its own time, in frequencies below the range of ordinary hearing. It is a reminder that not everything important is loud, not everything true announces itself with fanfare. Some of the most significant things in the universe are happening in silence or in frequencies we cannot naturally perceive, and they ask only for instruments delicate enough and observers patient enough to notice them. You don't need to be loud tonight. You don't need to figure anything out or arrive anywhere. You just need to be here, quiet and still, listening to whatever is present. Your breath, the soft sounds of wherever you are, the gradual slowing of your thoughts as sleep begins to reach up toward you. Let it come. It knows the way. And so, very gently, we come to the end of our journey tonight. We have traveled a long way together, from the surface of a brilliant blue planet at the edge of our solar system, down through layers of exotic ice and churning chemistry, all the way to a place where carbon transforms itself into something extraordinary, where diamonds fall like rain through the dark interior of a world that most of humanity has never once thought about. We've learned that diamond rain is real, that it was confirmed not so long ago by brilliant and patient scientists using some of the most remarkable instruments ever built, that it happens closer to the surface than anyone expected, and that this changes everything about how we understand Neptune. We've learned that the chemistry of it is quietly beautiful, that water and ammonia and the humble molecules of planetary ice all work together like collaborators to make something impossible seem inevitable. We've learned that carbon itself is one of the most extraordinary elements in the universe, that the same atom that makes the graphite in a pencil can, under the right conditions, become the hardest substance in nature, or something harder still, or a strange metallic ocean in which diamonds float like icebergs. We've learned that the falling diamonds warm the planet from within and drive its storms and stir its magnetic field into that beautiful, scrambled complexity that puzzled scientists for so long. And we've learned that one day, perhaps, we might be able to listen to it all, to hear in frequencies below the range of human hearing, the quiet and ancient sound of diamonds falling in the dark. It is, I think, one of the most wonderful stories in all of science, and I am so glad we got to share it tonight. Now the music will carry you the rest of the way. There is nothing more you need to think about, nothing to remember, nothing to solve, nothing to prepare for. Just let the sound wash over you and let your mind do whatever it would like to do. Wander or drift or simply dissolve into the quiet. Your brain is a remarkable thing. Give it the gift of stillness now and let it take you wherever it wants to go. Sleep well wherever you are in the world. You deserve rest. You deserve this. And we'll see you next time among the stars.